Okay, very good. Welcome everybody to this week's COVID-19 seminar, the mathematical modeling of COVID-19 seminar. We're very pleased this week to have a distinguished speaker, Dr. Ping Yan of the Public Health Agency of Canada. He has been a driving force in the recognition of the role of mathematical modeling in public health decision-making process. He has worked intensively with Canadian modelers in Canadian universities in modeling SARS and the pandemic influenza. And he's, of course, very active in the work that's going on now in the modeling of COVID-19. So Professor Dr. Yan, welcome to the seminar. We're happy to hear your talk on preliminary trend analysis of COVID-19 in 5 selected provinces based on data reported. Dr. Yan.
Okay, thank you, everyone, and good morning. And somebody advised me that in a PowerPoint, either put one picture that was 1,000 words, but never put 1,000 words with a picture together. But today, I think I'm going to break these rules. A lot of words and pictures. And I call this a preliminary analysis, which means that the results are not final. There are a lot of caveats. And I'm updating this analysis almost weekly. That means if I present the same thing next week, some of those statements or interpretations may change. So just keep in mind, it is a green product. And in this figure, I put 2 graphs from internet sources, and people may be quite familiar with. On the top right of the charts are the typical presentation we hear from the media all the time. Is the number of reported cases every day, which means it's by date of report. This is the most familiar trend everybody sees, and it's, you can go even to CTV or CBC, any news media, or the government media, you see the same graph. And so I put this from a dashboard from an ArcGIS company they call the National Dashboard, dated a few days ago. And on the bottom right, there is a chart of the similar color, blue, but a very different trend. And this one actually is also from the public available media from Canada.ca. It's directly from our agency. And the only difference between these two is the one on the top is by date of report. And the one on the bottom is a date of illness onset with a star, which I will explain a little bit later of that part. So basically, it's the same epidemic, the same people, but the totally different trend interpretation. For the first thing we know, there is a reporting delay. That means for each individual, there's a time from the illness onset for several days or even 10 days or 2 weeks before this person being diagnosed and reported and entered into one of the central registries. So if you see those 2 circles, these are almost the same shape, the same clusters of events. But if you look at the dates, they're at least about 10 days or 2 weeks apart. So that means reporting delays cause 2 problems. The first problem is about a 2-week delay of our knowledge of any major outbreaks. And this is quite consistent with what Dr. Tan has been saying at the very beginning of the pandemic, saying everything we see now possibly is a reflection of some event happened a week or 2 weeks in the past. So the other side of the story will be anything which might be happening today possibly will be reflected in our data maybe 10 days after. So this is one problem. Another problem is bias of the trend when you display by illness onset. You see there's a sharp decline at the end, and the government website put a gray zone to cover it because the number of cases with the recent date of onset are more underreported than cases with symptoms onset quite a while ago. So that gray zone in this presentation I want to unpack it to see if we could make any trend interpretation. That's the first part of the topic. And the phenomena, it's not just unique for COVID-19. So I put some historical stories from the past. For example, on the top right corner, were data on date of onset based on H1N1. Actually, it's in Ontario, in Canada, through the summer of 2019, 2009, 10 years ago. And as we see, the date of onset will always be added or revised when new data are coming in. And the same thing for the right bottom. These are the examples of the SARS 2003 in Toronto, in Hong Kong, in Singapore. A different color code. They're all based on date of onset, but reported at different period of time. And for the bottom left, I just so I'm familiar with this topic because that's my career started from there. I joined the workforce in 1992, and by year of onset of AIDS, I was working on AIDS surveillance data. The question was it really true we had only 600 some cases diagnosed in 1992 when we're still at the end of 1992? Now you see, if I use the data reported by the end of 1999, you see we had about more than 1,800 cases diagnosed in 1992. So it's the same phenomenon. So what we want to do is to unpack the trend in that gray zone. So that means we want to adjust for this reporting delay in order to get the trend. And that one, under a popular terminology today, we may call it a null cast. So for notations, if I'm using the subscript T for the time at onset of the event, and then it takes a delay of time X, get the event reported at that time, T plus X. I use a big C, refer to the current time at which we want to do the data analysis. So what we actually observe is NT given C. It's the number of onset at time T as reported as we are aware of. So the logic is the observed trend, NT given C, is always a proportion of the true trend by a weight. And to do the reporting delay adjustment becomes a problem to estimate this weight. If you know this weight, then we do the adjustment. So for data, we must be able to measure the delay for each case. And if we can do so, that event, saying onset at time T, as we see by time C, is equivalent to the event if we say the delay big X is less than or equal to C minus T. So these are two equivalent events. So the weight will be the probability of this event. And the statistic estimation becomes the estimation for this distribution of X, big X smaller than or equal to small x. A little bit complication in this, statistically we call it right truncation, because these reporting delays are not observed forwardly or randomly. It has to be reported first. And then you look back and the retrospective asserting what the date of onset is. So that gives a selection bias. So all the observations we observe as delays tend to be on the shorter end. And some individuals with a very long delay may be missed in this collection. So then there's a standard survival analysis technique to deal with the right truncated data. So I won't go too much details here, just to give you the method I use. Now it's a little bit complication here. Is the reason they put a date of yield onset star not all the cases are true symptom onset. And so they have an algorithm in this surveillance system. So basically, we prefer is a symptom onset. And there are a lot of missing fields in that field, not because they don't have symptoms, just because so many data and the people don't have time to retrospect to map out all the onset. So then they use a specimen collection date as a proxy, which may not be a good proxy, but that's what they do. A very, very few cases was a live confirmation date, but that is almost as small as negligible. So these are the what the onset star really means. And so, because in the methodology, we want to estimate the distribution of the delays. As you see, in some provinces, basically all those onset star is date of onset. And some provinces have a mix of both. Yet they do have a mixture of both. And my observation is the duration from a symptom onset to reporting is much longer, stochastically longer actually, than the duration of the green one, which is from a specimen collection to reporting. And so I will talk about this again later, but at least we know if we want to do a reporting delay adjustment, these two events do not follow the same delay distribution. We have to do separately. And because they are mutually exclusive, so by the end, I will add them together. And this is one example from one of the provinces. As you see, even with those cases with the date of onset, and not necessarily all the cases have a date of reporting. And that is a little bit a weakness in our data, which I've been discussing with the people in surveillance to make sure keep a good bookkeeping for every date of onset or any event. When you enter into the database, you have to stamp it, have to report it. But in spite of all the effort we're doing, possibly it's a lot of people involved and the huge caseload. And then in this case, there are a lot of cases, they have data of onset, but there's no data of reporting, they're missing. So we really have to jump a leap of faith using the reporting delay distribution calculated with a subset of data, assuming it is representative to all data, we do the adjustment. So that's what I show here. After that, as you see, we do a reporting delay adjustment based on symptom onset, which the data is represented by the blue bars. And then we do a reporting delay adjustment for those based on specimen collection date as represented by the orange bars. So the total date, excuse me. Okay, so the total number of by onset star is the stacked bars of these two. And then you get a very, very unstable reporting delay adjusted trend, which is the red. And then I run a 3-day moving average to smooth it or smooth them as overall. So this is basically the first part of this analysis. And there are caveats and limitations as usual. And first is I only present the point estimates here. And the method here is not actually new. It's back to the 1980s. And the early applications are used by the insurance companies. And I call that the actuaries method. And on top of that, over the years, a lot of advances in the statistical part. And then I have some papers listed here, like Brookmeyer and Null, and Lawless, and so on. And in this method, first for the confidence intervals, and then adjust for some other things, even including the random aspect and other things. They're available just And so one caveat in my experience is it is very sensitive when we're trying to do the null casting. It's really at ending point, it is rising or declining right now. And for that exact question, it apparently is very sensitive to any recent change in the reporting process. And so actually, I do not at the moment have full information about any of such changes. So we're still exploring, myself with my collaborators in academia, exploring different ways to account these issues. Another issue will be this method is really put a lot of emphasis on the reporting delay distribution that I put a label called X, but not fully utilizing the underlying disease process of transmission. And there are some people saying we should add this information to improve the null casting. Yeah, that needs to be done. And also, we realize in recent literatures that this kind of reporting delay adjustment has been gained a lot of attention recently. And so there are more work to be done. So that's another way I say this is really, really a rough preliminary analysis. Having done so, the next part of this presentation is, can we make one step further backwards? Because when we talk about the data onset, it's really one step closer to the transmission process compared to base by reporting. But the ultimate goal is to get the understanding of the transmission process by date at transmission. And that is something nobody can observe. There's no data can be collected on the exact moment of transmission. So what we do is we do something called the backcasting or back calculation, is to take into account of the incubation distribution we could learn from the literature from the time of infection or exposure to the time of onset. Okay, and that trend could be, I put the result first here, is on the top right, the red or the green trend, the green is a smooth line, is after reporting delay adjustment based on data onset, and then give something we call the null casting. And then using that one as the input again, including the incubation distribution to get something blue at the bottom. So then you get the three trends on the same chart and are several days apart. And now you would see the red one actually is the one by date of reporting. This is the most popular trend we see on the media all the time. And then the blue one is if my back calculation is anyway believable or interpretable, if something happened 10 or 15 days ago. It has a shape resemblance, but it moved quite a while ago. And the green one is somewhere in between. So now it's how to do it. The idea is actually not quite new. And I take this example from a different application I did in the past. So the idea is if we have input data as red circles, such as the data of onset, and then as an input, assuming it has some distribution with a mean, I call it DT, and that mean must be at each point is a weighted average or weighted sum of the past infections through a convolution. So that I is the incidence of infections, and then that F is the incubation distribution. So then we somehow not straightforward to deconvolute that formula, but using that convolution into some statistic method, such as the maximum likelihood, to estimate the parameters. And so in this particular example, I make some assumptions. First, is the incubation distribution. There is such a thing called the incubation distribution, which is a stationary, won't change over time. Then I take it as a log normal form for the incubation period with the 2 parameters. And then I parameterize them in such a way, one parameter is a median, the other parameter is a 95% quantile. And then I took this estimate from a recent literature that I can find. And then I put into a statistical algorithm. That's what I do. And then here are some results by time of transmission, some tentative results, let's say. So the thick blue line is a default, is a median of a little bit less than 5 days, and with a 95% rule of more than 12 days. And then there's some alternative hypothesis from the literature. How about the median was much shorter, like a 3.some days, or much longer, close to 6 days. And the quantile could be shorter, less than 10 days, could be as long as more than 19 days. So I found all those things and run many, many alternative hypotheses. Those are the thin lines to see what that kind of sensitivity for the result. And here are, as you see, I put one of those lines several pages ago. I put here are in selected provinces. As I said, the red line is the most visible line from the media we see from the public sources everywhere. It's a red one. And it is smooth. This one is smooth by 3-day running average. And the blue one is the closest in meaning to the data of transmission, provided my calculations are correct. And then the green one is in between by data of onset. Now it's time to talk about, again, caveats and the limitations. And first, in the current analysis, we assume there is such a thing called the incubation period. It's a stationary and it's a log normal. And then I may want to say a little bit on why I choose a log normal, not a gamma or not a variable or other things. There's quite some literature since the 1960s and recently reviewed in 2007 and looks a lot, like I'm talking about in 20 or more different acute communicable diseases. And they looked at the incubation period through epidemiology link and everything, and find that the log normal distribution tend to be the best fit against other models. Why is that so? I think it's a little beyond this topic, but I just take that as log normal. And the log normal distribution has a feature that's quite skewed with a very long tail. And that is empirically supported by evidence we hear from the media even. For the incubation period for COVID-19, on one hand, they're not too long. The median is around 5 days. But on the other hand, there are a lot of outliers, so-called, at the very tail end. I think there's some countries out there as long as 14 days or even 24 days. I don't know if there's an outlier longer than that. So that is a typical shape of something like log normal as well. And with the range of parameters, I did a little bit of sensitivity analysis, as you have seen. Another caveat is similar to the reporting delay again. Yes, we want to know the trend near the end as recent as possible. And unfortunately, the more recent it is, the more sensitive it becomes to the last data point we use. So a tiny jump up and down for the last data point will give a lot of variations at the tail. And that's one of the reasons I truncated a few days of the blue curve, because I don't quite believe what is as reason. One of the reasons could be, since we talk about an incubation period distribution, of course, it's more information about something happened a long time ago. The more recent it is, according to that distribution, the data have less information about it. And also, as before, I did not provide a confidence limit. but it is also doable, at least in a different application I made on HIV/AIDS. I did a lot of resampling and bootstrapping, and it's a doable, just time consuming, so not presented. And this is another caveat. Again, back to this on-site star issue. In order to make as many data as possible, and I follow the common practice of many other people, like epidemiologists, that they lump the specimen collection as a proxy of symptom onset. And as time goes by, over time, I start to realize that it's not really a good proxy. And so if I do a reporting delay adjustment for the total and do the back calculation, it may be problematic to interpret the trends. But the good news is, over time, for many provinces, a lot of cases previously classified on-site star equal to specimen collection are updated to their true symptom onset date, which means it takes people a lot of time actually to review all the data to retrospective ascertain the date of onset. But we're moving to the good direction. As you see, in some provinces, the date by specimen onset now is minimum, if not zero. And so for these provinces, the back calculation results are more interpretable than provinces still with a lot of mixed bag. But I hope as time goes by, this interpretation will get better and better over time. Of course, the last caveat is whatever I present here, we're assuming the transmission of this event will be eventually become symptomatic and will be diagnosed and reported. So it may not be representative of all the transmission events if we think if there were a lot of asymptomatics, and that is again beyond this approach. So these are all the limitations. So before I conclude, I just put some curiosity. These are not results. It's just my personal curiosity, since the Fields Institute is a mathematical institute, a lot of mathematical modelers, we could brainstorm with it. And so here I put all those results together from different provinces and created this kind of graphs. And first, we see sort of a periodicity of the small waves. We could imagine one part is could be artifact of the algorithm I'm using. But I'm more thinking it's really the outbreak is a sum of smaller outbreaks in clusters in concentrated regions. You're adding them up. There's a composite picture within each jurisdiction, within each outbreak. But again, there's a synchronization as well, loosely. And so I just put there. So why it is so, or it's just coincidence. And then if you look further, it's from other events I did, I found the same thing. At the very beginning of the pandemic, before we had a bigger problem in Canada, I was mainly focusing on early outbreaks in Singapore and Hong Kong. And it's a very, very nice synchronization there. And then in 2009, in the summer, I did a similar analysis, compare the outbreak of H1N1 in Mexico with that in Canada. We do have a very, very different timing of the major waves, but those small waves are synchronized pretty well. Even further back to SARS, I put that chart for the international comparisons of the different countries and regions. A similar thing. So again, it's a curiosity. And then to interpret, of course, the most direct or intuitive way of thinking is the outbreak is actually happening in a very patchy environment. As I said, it's a composition of small clusters. we may want to unpack that curve and using some kind of meta-population models. For example, the 2003 SARS in Toronto, I was able to unpack a little bit empirically. For example, the big green was a hospital transmission. The first big wave in 2 hospitals. The second big wave is in 1 hospital in North York. And then under the small outbreaks, one was a household transmission, the other was a famous church group back then. And so you see how those patches are added up to those small waves. But that may be just only one of the many possible interpretations. For example, even assuming homogeneous mix without those patches or anything, just a simple basic SEIR with ODEs. If I experiment something, say the latent periods and infectious periods are not exponentially distributed, for example, Ireland distribution, with a very, very small variations, and then the result won't be a typical bell-shaped smooth curve anymore, but more likely something on the right side. So that's my just experiment. And these are all those ordinary ODE models on simple SEIRs, nothing special. You could create very similar waves. So that's another possibility. Or the third is the interaction of the two. So there's a generation effect like this, and then there's a patchy environment and heterogeneity and cluster effect. And can we build a model to explore how these things are enhancing each other? These are just for mathematical modeling on the deterministic side. And for those with stochastical models or accounting processes or homogeneous or non-homogeneous mixture of Poisson processes, I found some literature talking about the similar applications and events from insurance claims to DNA to other things. So that means to end this topic is that every, as they say, every disaster also opens an opportunity, and possibly we could also broaden our fields and looking at the other applications and find any commonalities. And there's a lot of modeling to do. So that's the end of my